In this first video for Chapter 22, we will talk about naming amines, their physical properties, their basicity, and a brief review of the synthesis of amines. We'll start by learning the rules for naming primary amines. A primary amine is when you have an amine that is attached to one R group, so that's what makes it a primary. Now there's two types of names we can have for amines. There's the common names, and with common names you name the R group as an alkyl group followed by the word amine. For the systematic name or the IUPAC name, we use amine as a suffix for the parent chain, so that's more similar to the rules that we learned for naming other functional groups. So we'll go ahead and start with the common name. In this amine, we have a 2-carbon chain attached, and so this is called an ethyl group. So our common name for this molecule is simply ethylamine. For the systematic name, our parent chain is going to be 2 carbons long. Okay, so that's usually an ethane group. Now what we're going to do is we're going to remove the E and replace it with amine as our suffix. So this becomes ethanamine. Okay, so with the systematic name, you really focus on that longest chain of carbons again. With secondary amines, the nitrogen is bound to 2 R groups. So for the common name for secondary amines, you name both of those groups as alkyl group, followed by amine. Now the 2 alkyl groups are placed in alphabetical order, and if they are identical, we use prefixes such as di, tri, etc. Now in the case of secondary amines, we would use the prefix di, meaning 2. For the systematic name, we choose the longest chain as the main chain, and we designate the other group attached as an N substituent. Again, we use amine as the suffix for the parent chain. So we have 2 examples here that we'll go ahead and go through. Let's start with the common name for our first example. So in this secondary amine, we have a 3-carbon group, which is a propyl group. We also have a 1-carbon group, which is a methyl group. So we'll put these 2 substituents in alphabetical order. So we get methyl, propyl, amine, and this is all one word. Now for our systematic naming, we are going to have our longest chain as the 3-carbon chain. So this is our propane chain. Now the methyl group is going to be called an N-methyl. And that's because the methyl group is directly attached to the nitrogen and not attached to any carbons. So we'll go ahead and call this N-methyl propane. Then we're going to take off the E and replace it with amine. So we get N-methyl propanamine. For our second example, we have an isopropyl group. That's because the nitrogen is attached to the middle carbon. We also have a methyl group. So our common name will be isopropyl methyl amine. Now with our systematic name, our main chain is going to be this propane group. Now the nitrogen is not attached at the very end, it's actually attached at carbon number 2 of our longest chain. So we're going to have to show that in our name. Then again, we have a methyl group attached to the nitrogen, so that's our N-methyl group. So our systematic name for this molecule is going to be N-methyl 2-propanamine. And again, this 2 is just showing that the nitrogen is attached to carbon number 2 rather than carbon number 1 and having it be a long chain. With tertiary amines, we follow the same rules as with secondary amines. Now with tertiary amines, since the nitrogen is bound to 3 R groups, we would put all 3 R groups as an alkyl group, alkyl, alkyl. And again, that's going to be in alphabetical order. We use prefixes whenever 2 of the alkyl groups are the same. For the systematic name, again, we're going to choose the longest chain as the main chain, and we'll designate the other groups as N substituents, using amine as a suffix for the parent chain. So let's go ahead and do the common name for this tertiary amine. So we have a 3-carbon chain, which is a propyl group, 2-carbon chain, which is ethyl, and 1 carbon, which is methyl. So we'll start by putting those in alphabetical order. And finish with the name amine. For our systematic name, our longest chain is going to be this propane chain. And then we have an ethyl group attached, which will be an N-ethyl, and a methyl group attached, which will be an N-methyl. So again, we'll go ahead and put those in alphabetical order. We get N-ethyl, N-methyl, propane, take off the E, and replace it with amine. Sometimes an amine can act as a substituent, and when it is a substituent, it's called an amino group. So for instance, with this aldehyde, the amine is simply a substituent. It's just hanging off of the main chain. So we're going to go through the process of naming aldehydes as we've learned so far. So we'll start by numbering the longest chain of carbons, giving number 1 to the carbonyl. Now, our amine group is on carbon number 3. So we're going to go ahead and write 3-amino. And then for our name for a 3-carbon containing aldehyde, it's propanol, 3-amino propanol. The main cyclic amine I want to highlight is aniline, and we've seen this before in our aromatics chapter. So the name aniline is the common name for this compound. The systematic name is benzenamine, and that would be naming this molecule in terms of it being an amine. So next, I briefly want to go over heterocyclic amines. And heterocyclic amines occur when the nitrogen is incorporated into the ring. We've seen a lot of these compounds before in the aromatics chapter. Now, these heterocyclic amines mainly go by their common names. So pyrrole, pyrazole, and indole are the common names for all 3 of these compounds. But I briefly want to go over the systematic names. Now, you will not need to know either the common or the systematic names for any quizzes or exams, but it's interesting information to have. So the systematic name for pyrrole is 1-aza cyclopenta 2,4-diene. Now this term aza means that a nitrogen has replaced a carbon within the ring. So this 1-aza means that we've replaced the carbon number 1. So we can go ahead and actually number this, giving number 1 to the nitrogen. So this 1-aza means the nitrogen has replaced carbon number 1. The cyclo means it's a cyclic structure. The penta means that there's 5 atoms within the ring. And the 2,4-diene are where the double bonds start. So we have one double bond starting at carbon 2 and the second starting at carbon 4. For pyrazole, which contains 2 nitrogens, its systematic name is 1,2-diaza cyclopenta 2,4-diene. So again, numbering the carbons or the atoms, we have carbons 1 and 2 replaced with 2 nitrogens. So that's where we get the 1,2-diaza. Again, cyclo is cyclic, penta is 5 atoms, and 2,4-diene is the location of the double bonds. As far as the physical properties of amines, amines are considered moderately polar, and that's because of the presence of an electronegative nitrogen atom. As far as the boiling points of amines tend to be higher than alkanes, which are made up only of carbons and hydrogens, but lower than that of alcohols. So alcohols, which have OH groups, are capable of hydrogen bonding just as much as an amine. However, a hydrogen bond with an oxygen is stronger than the hydrogen bond with a nitrogen. Now, whenever we're comparing boiling points of different types of functional groups, we always have to compare structures that have similar molecular weights, since molecular weight can influence boiling point as well. Now, in general, primary and secondary amines have higher boiling points and solubility in water than tertiary amines, and that's because of the presence of H's. So with a primary amine, you have two NH bonds, which are capable of hydrogen bonding. And they can both be hydrogen bond donors and acceptors. With a secondary amine, let me redraw that. With a secondary amine, we also have an NH bond, but only one. So this can hydrogen bond, donate, and accept, but still it's a little bit less than a primary amine. With a tertiary amine, because the nitrogen is bound to 3 R groups, there are no NH bonds. So this cannot be a hydrogen bond donor. However, it can be a hydrogen bond acceptor. So in general, with tertiary amines, they have lower boiling points than primary and secondary amines, but they still have some solubility in water because they can accept hydrogen bonds from water. However, they cannot hydrogen bond with, or they cannot donate a hydrogen bond to water. Now, as far as the structure of amines, when nitrogen is bound to 3 R groups, and this can be either hydrogens or carbons or other atoms, as well as a lone pair, this is when nitrogen is sp3 hybridized. Okay, so in sp3 hybridization, we have 4 hybridized orbitals. Now, if we consider nitrogen gives 5 valence electrons to any sort of molecule, we'll take those 5 valence electrons and distribute them. So this is how those electrons are distributed in all of the orbitals. So these paired up ones here represent the lone pair. The rest of the unpaired electrons are capable of forming bonds with other atoms. And last, we'll talk about chirality. So we learned with carbons that carbon can be chiral if they're attached to 4 different things. Now, a nitrogen can also be chiral if it's attached to 3 different groups, and that's because the lone pair can count as the 4th group, and so if it's bound to 4 different things, it makes it chiral. Now, the difference between nitrogen and carbon has to do with their geometry. So with nitrogen, we have trigonal pyramidal shape around the nitrogen atom. Now, with this trigonal pyramidal shape, it can actually flip back and forth. This is the enantiomer of this molecule here. But since these guys are going back and forth so much and so fast, we actually always have a racemic mixture. So this is known as pyramidal interconversion. And with this pyramidal interconversion, we're not capable of isolating each enantiomer separately because they're going to constantly flip back and forth between one another. Now, carbon does not exhibit this type of property. This is only for nitrogen. But still, nitrogen does have chirality. Now, in general, amines are known as being bases and nucleophiles. Now, in general, amines are relatively weak bases. While they're stronger than water, they are weaker than hydroxide or alkoxide. So with these ones, we have negative charges, which makes them much stronger bases. Now with amines, to evaluate the basicity, we actually look at the pKa values of the conjugate acids, and these are known as the aminium ions. So these are the conjugate acids that form after the amine has acted as a base. So let's go ahead and take a look at the Ka expression for this aminium ion here. Now this aminium ion formed when this amine acted as a base. Okay, so now we're looking at the aminium ion acting as a conjugate acid. So in general, it would give up its proton and reform the basic amine as well as the hydronium ion. Now the Ka expression for this reaction is this. We have the aminium ion in the denominator and then we have the amine in the numerator. Now in general, a small Ka represents a more basic amine, and this more basic amine means that the reaction lies to the left. So for an amine to be more basic, it means that it's more likely to be protonated and exist in the iminium ion form. So a small Ka means that there's a higher concentration of iminium ion, which represents a larger or stronger base. Now a small Ka corresponds to a large pKa for the iminium ion. So the main thing you need to take away from this is that the higher the pKa corresponding to an amine, the more basic it is. Another way of evaluating basicity is we can look at the amine's willingness to give up its lone pair, or we can look at the stability of the iminium ion. So let's go ahead and look at ammonia, our simplest amine. Now, in the presence of an acidic proton, the nitrogen will go and grab that proton, and we will create an ammonium ion. Now, ammonium has a pKa of around 9.26. Now let's take a look at a slightly different amine. We'll look at a primary amine that has an ethyl group attached. Again, putting it in the presence of an acidic proton, we will protonate it and create the iminium ion. Now this iminium ion has a pKa of around 10.75. So the higher pKa means that this molecule is more basic. And when we're talking about more basic, we're talking about the amine. Now what makes this more basic than the ammonium has to do with the R groups here. So we learned that alkyl groups are weakly activating. They donate a little bit of electron density. We saw this a lot with carbocations as well. So these electrons can actually donate, or these carbons can donate some of their electron density and stabilize the positive charge. Ammonium doesn't have that. Hydrogens are not capable of donating any electron density. So this slight donation is going to stabilize this positive charge and make it more likely to form. So that's why we see a slightly higher pKa. Now in general, the stabilization of alkyl groups is not great. So the difference between ammonia versus primary amines versus secondary versus tertiary is not a very big difference. For all of these types of amines, they'll all have pKa's of around 9 to 11. So on the next few slides, we'll look at different types of amines and see how these are going to compare to typical alkyl amines. So aryl amines, which are, for example, aniline, are weaker bases than alkyl amines, and that's for two reasons. The first reason is the lone pair on the nitrogen are involved with resonance with the benzene ring. And the second reason, which is related, is the conjugate acid would actually decrease the number of resonance structures. So if we were to put aniline in the presence of an acidic hydrogen and protonate that nitrogen, we would form the iminium ion. Now there's no lone pairs on the nitrogen that can participate in resonance with the ring. So we've decreased the number of resonance structures that can exist. So the pKa for this iminium ion is about 4.58. Now if we compare that to a regular alkyl amine, such as an amine attached to a cyclohexane ring, protonating this wouldn't change the structure very much. And in fact, the ring would provide stabilization to the positive charge. So that's why we see higher pKa's for the alkyl groups, around 10.64. Non-aromatic heterocyclic amines have similar basicities to acyclic alkyl amines. So if we look at an example of a non-aromatic heterocyclic amine, we have this molecule here. This has the common name of piperidine. Now the nitrogen in this molecule is sp3 hybridized, and really it's attached to two R groups, so we can consider it secondary. The only difference is all of the carbons are connected to one another. So the pKa of piperidine is around 11.2, so it's about the same as regular alkyl amines. Now let's take a look at aromatic heterocyclic amines. And in general, these types of molecules are less basic than alkyl amines. So we'll look at two examples. One is going to be the molecule pyridine, and the other will be the molecule pyrrole. And we've seen this concept a lot in the aromatics chapter. So let's consider both of the lone pairs of these nitrogens. Now for pyridine, these lone pair are localized. They are not necessary for aromaticity because the molecule already has 6 pi electrons. So even though these lone pair are sitting here on the nitrogen, they're not a part of the aromaticity of the ring. So the iminium ion for pyridine has a pKa of around 5.23. Now the reason that this pKa is lower than that of the alkyl amines is because the lone pair are located in an sp2 hybridized orbital. With sp2 hybridization, the lone pair are closer to the nucleus of the nitrogen than would normally be for an sp3 hybridization. That's because we have more S character in sp2 hybridization. So since these lone pairs are held closer to the nucleus of the nitrogen, they're less willing to go out and be donated to other atoms. So anytime we're comparing something where the lone pairs are in sp2 versus an sp3 hybridized orbital, the sp3 is typically going to be more basic because the lone pairs are held further from the nucleus of the atom. Now in pyrrole, these lone pairs are absolutely necessary for aromaticity. Without them, the molecule would only have 4 pi electrons, and we need to follow Huckel's rule in order to have 6 electrons in order for the ring to be aromatic. So by donating these lone pair to the ring, we have a total of 6 pi electrons, which will make the ring aromatic. So these lone pairs are currently delocalized. They are occupied, which is going to make them less willing to be given up. So if we were to look at the pKa for the corresponding iminium ion of pyrrole, we would find that it has a value of 0.40, which essentially means it's not basic at all. So amides are also not basic at all. Let's go ahead and take a look at just a regular amide structure. So amides are capable of resonance. We can have the electrons come up onto oxygen, creating a positive charge on the carbonyl, and then the nitrogen can donate its electrons over to create a third resonance structure. Now, if we were to take this same amide and protonate the nitrogen instead, we would create an aminium ion where we have the positive charge on the nitrogen. Now, if we were to attempt to do resonance again with the amide, we would create a structure where we have two positive charges right next to one another. This cannot exist. It is too unstable. So by protonating this nitrogen, we essentially decrease the number of resonance structures that can exist for an amide. So we've gone from something that can have 1, 2, 3 resonance structures to one that's stuck in a single structure. So as a result, we're not going to protonate this nitrogen. And in fact, with amides, the oxygen is more basic than the nitrogen. So in the presence of an acidic proton, the oxygen's lone pairs would actually grab the acidic proton which would form a conjugate acid that is stabilized by resonance. So we actually get 3 resonance structures by protonating the oxygen. So with amides, this is much more favorable than this occurring. Now let's do a series of practice problems where we're going to circle the strongest base of each pair. Now all of these structures are drawn in bond line structures, so I did not show the lone pairs on each of the nitrogen atoms. So I suggest that you draw the lone pairs and then evaluate them and choose the strongest base. Now I invite you to pause the video, attempt these problems on your own, and then restart the video to check your answers. So for our first problem, we have 2 tertiary amines. Each of those nitrogens has a lone pair. Now the difference with the second molecule is that this lone pair is 1 bond away from a double bond. So we have an allylic lone pair. And these allylic lone pair can participate in resonance. So as a result, these lone pair are going to be occupied in resonance, whereas these ones are just going to be hanging out, ready to act as a base. So that's going to make our first molecule the strongest base. For our second set, we have 2 molecules that look like aromatic rings. Now let's go ahead and evaluate each of these rings for the potential for aromaticity. Now for this first one, we have 5 atoms and we have 4 pi electrons. Now we need 6 pi electrons in order to be aromatic. So if these were to be donated to the ring, it would make the molecule aromatic. So these lone pairs are currently occupied in aromaticity. For this molecule, we have 7 atoms and we have 6 pi electrons. Now, if this nitrogen were to be sp2 hybridized, it would donate the lone pair to the ring and would give a total of 8 pi electrons, which would make the molecule anti-aromatic. So we don't want to make a molecule anti-aromatic, so that means that this nitrogen is going to remain sp3 hybridized. Now, even though these lone pairs can participate in resonance, they're not participating in aromaticity, which is much stronger. So as a result, our second molecule is going to be more basic. For our third set, we have our lone pairs. Now, if you look closely, we have an amide functional group here. So even though it's in a ring, we have a carbonyl directly connected to a nitrogen. So amides are not basic at all. So instead, our first molecule is going to be the most basic, and this is just a regular tertiary amine. For problem set 4, we're again looking at aromatic rings. Now for our first molecule, we currently have 2 rings fused together, and we have 2, 4, 6, 8 pi electrons. Now if this nitrogen were to donate its electrons, we would have a total of 10, which would meet Huckel's rule. So these electrons are necessary for aromaticity. Over here, we again have 2 rings fused together. We can see that we have a total of 2, 4, 6, 8, 10 pi electrons without the lone pair here. So these lone pair are actually localized. They're not participating in aromaticity like we have for the first compound. So that's going to make a second one more basic. For problem 5, we have 2 amines on benzene rings. Now this is a nitro group. A nitro group is not an amine, even though it contains a nitrogen. But we've learned that nitro groups are strong electron withdrawing groups, whereas OMe groups are electron donating groups. So let's consider these lone pairs on our nitrogen, and we'll look at the first molecule. So we know that they can participate in resonance with the benzene ring. They can also participate in resonance with the nitro group, and the nitro group is going to withdraw those lone pairs towards itself. For the OMe group, even though we have resonance between the nitrogen and the benzene ring, the OMe is going to provide electrons that can help stabilize a positive charge that may form on the nitrogen when it takes an H. So any benzene ring that contains electron donating groups is actually going to make the ring more basic than a ring containing an electron withdrawing group. So we'll go ahead and circle this as our more basic molecule. And finally, we have a pair of molecules. We have a set of lone pair that are localized. They're not involved in the aromaticity of the molecule. And this is just a regular primary amine. Now the difference between these two is going to come down to their hybridization. What type of orbitals are the lone pairs located in? So these ones are located in sp2 hybridized orbital. These are sp3. So remember that any orbital that has more p character is going to have the electrons held further from the nucleus, which will make them more basic. So that's going to make this molecule the more basic of our pair. Lastly, I just wanted to go over a brief review of the synthesis of amines. So we've learned that we can make amines from nitriles. Now nitriles can be prepared from alkyl halides, treating them with sodium cyanide. The cyanide ion will come in and attack the carbon and kick off the bromine in an SN2 mechanism. From there, nitriles can be reduced to amines by using excess LEH followed by water. That's going to get rid of the pi bonds altogether and replace them with hydrogens. We can perform a similar reaction from amides. So amides can be prepared from carboxylic acids, treating them with thionyl chloride followed by excess ammonia. So here we have our amide, and amides can be reduced just like nitriles using excess lithium aluminum hydride followed by water to get an amine. And lastly, we learned how to prepare aniline back in our aromatic substitution reaction chapter. So starting with benzene, we can treat it with nitric acid conditions and do a nitration to put a nitro group. Then we can reduce the nitro group to an amine using hydrogenation or metal with hydronium followed by a base. So these are all reactions that we've learned in the past, but these are all ways to make amines. In the next video, we'll go over some new reactions. However, we will not need to know these reactions for exam 3. You'll need to know those for the final exam.